I'm Nish, and I'm the founding engineer of Color Genomics, where we provide a physician-ordered genetic test for the risk of getting various types of cancer. And historically, it's been very difficult to get this kind of testing done, so we focus on increasing access in a responsible way. And what I mean by that is working with regulation and providing genetic counseling with every result that we return. And our test costs $250. And prior to us, getting a similar kind of test done could cost up to $4,000. So that's me and what the company's about. And I'm kind of curious to get to know who I'm talking to a little bit. And maybe by a quick show of hands, how many people in the audience, I'm curious, are you guys data scientists? Raise your hand if you're like a data scientist type of role. Cool, most of you, that's cool. What about like, would you classify, how many of you would classify yourself as a bioinformatics person? And there might be some overlap there. Cool, a handful. Data infrastructure engineers or software engineers or something, a few of those. Anything else I missed, just raise your hand if there's something else completely. All right, cool. And all right, so that helps me kind of level set, get a sense of who I'm talking to. For most of you, I believe you all have the power to advance the field of genomics, and I'm hopefully going to convince you of that and show you how you can do that. But first, let's talk about how things are done today. So the field of genomics is quite nascent out of academia. The way problems are solved in an academic setting, where publishing kind of drives a lot of the incentives, is very different from industry. And that the shift has been relatively slow to happen in the field of biology and in genomics, but it is starting to happen. And it's making things very interesting. So I'm going to point out a few ways in which the genomics industry has room to grow and how you can help get us there. And also, if you'll humor me, I believe bioinformatics has many parallels to the field of computer security. So along the way, I'm going to point out what some of those similarities are, and hopefully inspire and show you what's possible by drawing a parallel to how this has been done in a different field. So let's get to the first theme, which is awareness and access. So awareness of genetic testing and access to it is small today, but it's starting to grow. Genetics is a powerful tool for assessing one's risk of getting a hereditary disease. But the standard of care is to actually look at the family history to see what one's risk is of getting a hereditary disease. Now at best, this is, if you just use the family history, this is at best a proxy for the patient's actual risk, which is largely influenced by their genetics. So the patient may have inherited a gene that drove their relative's cancer, for example, or they may not have. Conversely, the relative's cancer might not even have been driven by a genetic predisposition. They may have even had a high-risk mutation, but the effect of it may have been masked in the family history. So a common example of this is a woman who is at risk of getting breast cancer because she carries a BRCA1 mutation, which she inherited from her father. And because her father was male, the disease didn't show up in the family history. So for such people, these people might be at risk or they might not, and they have no way of looking at that without actually looking at the DNA. So today, for many people, this is pretty much the standard of care in terms of assessing one's risk of getting disease. So clearly, using DNA as the primary source of risk information is inevitable, and things are starting to look promising. Perhaps this chart's pretty familiar to you. The cost of genetic sequencing has dropped over time at a very rapid clip. And you notice that this graph is actually a semi-log plot. So Moore's law, which is actually an exponential law, is a straight line on this plot. And the cost of genetic sequencing is dropping actually much faster than that. So this shift coincides with the development of next-generation sequencing techniques, which I'll go into a bit more detail later on. Additionally, public awareness of genetic testing is increasing, thanks in part to legislation, as well as public discourse. More than any scientific advancement, though, it's been actually Angelina Jolie's decision to get tested for the BRCA1 and 2 mutations that has driven awareness and demand for this type of genetic testing in a way that's to be more broadly accessible. And since then, a national and global conversation has been kicked off that has significantly heightened the public profile of genetic testing as a viable option for people. And there is significant momentum for a shift in how genetic testing is done, making now an ideal time to have a large impact on how it will be done in the future. So to draw a parallel to the computer security world, let's go back to 2010. And so this is the facebook.com homepage. And the thing to notice about this screenshot, which this isn't my profile, I took it from the internet, is the URL bar. So back in 2010, everyone knew that SSL and HTTPS was something you should be using if you're a website operator. But very few people did, citing performance, kind of vague performance complaints, as well as complexity of implementation. So this is the way things were for a while. And then there was a browser extension called Firesheep that was announced. And this is what it looked like. Basically, you'd have your Firefox window open, and you'd be able to open up this sidebar. And basically, it shows you social media profiles of people who are logged into these websites on the same wireless network as you. So you'd literally be able to see which of your neighbors is logged into Facebook, into Google, whatever it is. And this was always possible. It's just that this browser extension made it very easy to see to see what was going on. So all you'd have to do with this extension is just click on one of these, and you'd be logged in as them. So obviously, this was a little bit surprising to some people, but nothing had changed in terms of the technology. This was a pure awareness play. And it worked. So very soon after this pretty simple hack was released, Twitter as well as Facebook made at least enabled HTTPS by default. And now we've kind of come to accept it. It's about 6 years later, and I think most people would be pretty surprised if their bank or any major service they use on the internet that did not use HTTPS. So I think the awareness of genomics is kind of following a similar parallel path, and we're seeing that happen right now. The next theme I wanted to go through is data sharing. So it's currently the case that many companies treat human variation data as a trade secret. There are even some public companies that use this data to partially justify their valuation. However, as time goes on and everyone will get access to cheap genetic sequencing, this proprietary information on variant frequencies will no longer be special. And it's just a matter of time until that happens. By holding onto this data, these organizations are delaying the progress of scientific advancement and the accessibility of actionable clinical testing. And this is kind of where the title of my talk comes from. If a company is collecting large amounts of data, they kind of have a responsibility to use it in a way that's actually helpful for humanity and not holding us back or being harmful. Thankfully, there's a huge movement across companies that are typically competitors pushing to collaborate and share this data. This slide is just an example of the types of data that I'm talking about, variant frequencies as well as specific mutations. Many companies are pushing to share this data and contribute to public databases such as ClinVar, of which here's a quick screenshot of that. And in the end, the data should not be a competitive differentiator, but it should rather be used to help everyone move forward together. The real differentiator should be the quality of the test or the service that the company is providing. And the data itself, as I said, should serve to move humanity's understanding forward. And to draw the security comparison again, these days when a security vulnerability is found that puts the internet's safety at risk, there's a set of organizations that make it very easy for people to collaborate across companies to make everyone safe. And we've even seen marketing efforts around vulnerabilities that make sure this information gets to people very quickly. To highlight two programs that are helping with this, there's Facebook's Threat Exchange, which is a program where companies can share information on malware and security threats with each other very seamlessly. As well as in February, President Obama signed an executive order encouraging companies to share more data on security threats. Genomics is seeing a very similar shift, and I think the kind of the precision medicine initiative ties into this very closely. Organizations are being pushed to share information more broadly. So next I'm going to talk about software and data formats and how all of you can help. If we are to generate useful data to push our understanding of science and genomics forward, we're going to need performant and maintainable tools for analysis of data at large scale. Much of the software used for genomics and most bioinformatics software in general has its roots in academia. So a typical development trajectory is that a lab or a grad student might build a useful data analysis tool and even open source it. And this tool will get dropped in as is in many genetic testing companies. But because these companies don't have a strong culture of engineering or open source, these tools won't be contributed back to. It doesn't always happen this way, but it is a very common occurrence. And as a result, the project gets maintained either by that single grad student or by that lab, or by nobody if the grad student graduates and there's nobody left to maintain this tool. So there have been exceptions, but as I said, but this model is still very common. And I believe the solution here is for software companies or rather for genomics and medical companies to look less like this and a little bit more like these. What I mean by that is that they need to have strong engineering cultures that foster development of high-quality open-source tools. And in the same way that companies like the ones listed here spend resources building and maintaining open-source tools that really the whole internet relies on. Companies in our space, in the genetic space, will also need to spend time giving back to these tools and improving it to make them better for everyone. Some companies in the space are starting to do this, but we will have a ways to go until this practice is commonplace. And I would like to say not all is bad, and there have been a few really good examples of things being done right. Now let's dive into some of these success stories in bioinformatics, and specifically let's focus on the problem of sequence alignment. Some of you may already be pretty familiar with this, but some of you may not be, so I'll go do a quick overview. So to cover really quickly how next-generation DNA sequencing is done, basically you have your DNA, and it gets sheared into many small pieces. And these small pieces basically get sequenced by a sequencer. It's basically a machine that you purchase. And the output of this sequencer are these small reads of like 150 base pairs. So a very common, so the raw data that you get essentially looks like this. It's this kind of text format, and it includes that thing in the blue is the actual sequence data, and the red is the rest of the read data. So to talk about the alignment problem, basically you're trying to figure out where in the genome these things go. And we can talk about the algorithm, but we don't really have time for that. So instead we'll talk about the format used to hold this data. The first one is called the SAM format. And as file says here, it's an ASCII text format with very long lines, which it is. That's what it looks like. It's a text format. It's not the friendliest format to use, but the text is there if you need to debug something or figure out what's going on. So this was the first version. They also released a companion version called BAM, which is a binary version of the text format. And basically what this is it's the same as that format I just showed you, but they've taken blocks of it and they've gzipped the blocks. So it's in this bgzip format or block gzip format. And the advantage of this, it sounds like a pretty small change, but the advantage is, one, it's a lot smaller, obviously. But two, because it's done in blocks, you can actually index it. And when you're able to index it, you're able to have visualization tools like this that let you kind of jump to any region in the genome and see what the alignment looks like in O of 1 time instead of O of n time. The more subtle thing that this allows for is for doing this kind of operation over the internet. So you could imagine a client and a server where the server is serving both the alignment as well as the index. And all you need to do is fetch the index, and you can do an HTTP range request for just the data that you need. So you're not downloading the whole maybe 10 gigabytes of data. You're only downloading 16 kilobytes. And there's a tool called IGV.js, and here's a quick example of that live being used. And the main thing there's a lot going on here, but the main thing to look at is those 206 requests at the bottom and the 64 kilobyte response sizes that show that we're only fetching the data that we need. Atom is another tool that's used that's kind of going a step beyond the BAM format of sequence alignment. I've heard it come up in a few talks at this conference, which is great. It basically allows you to query your alignments in a way that the BAM format just isn't very amenable to. So it stores data in a columnar format, so you can make queries across all of the reads in a position, whereas with a BAM format, that might be prohibitively expensive. And another step forward is Google Genomics, which has been kind of offering a nice REST interface to this kind of data as well. And all we did here, I should note, is compress and index the original format and then move it behind an API. So this is all the kind of stuff that you all are familiar with doing, and there's still a lot of low-hanging fruit in terms of further progress to be made. To draw the security analogy really quickly, I was going to compare it to PGP, which it's this tool that kind of came out of an academic setting, but it's still used. But because so many smart software engineers have been thrown at the problem of making encryption usable, it has become more usable, both for, this is an example of how it's not usable, but both for developers as well as for end users. End-to-end encryption has become much simpler. And this is a quick example of one place in which we have yet to improve, which is the variant call format. So we're still storing our genetic variants in a format that's text-based. So there's definitely a lot of room to be improved here as well. So to conclude, it's an exciting time for genomics. The technology and our ability to read DNA is getting better by the day, but analyzing the data remains a strong challenge. Data initiatives to get people tested as well as to share data are lending lots of momentum to this field, which is making it an exciting time to enter now. And I'll close with this quote: "The best way to complain is to create." And wanted to say thanks to Data by the Bay, but also to all of you guys for giving me your attention and time. And if any of what I've talked about sounds interesting, my company, Color Genomics, is hiring, or just feel free to get in touch with me and talk about this stuff. All right, thank you very much.
I think we've got to head for the next talk at the moment, but hopefully Nish will be around for
Sure, yeah, happy to answer questions in person.
Fantastic. Oh, cool. Okay, great.
All right. All right, well, I'll be around afterwards too. Great, thank you so much.